Hello everyone, my name is Damien Duffy. I'm a chemical engineer and team lead in small molecule process development at APC Dublin in Ireland. And today I'm going to be giving a talk on the development of a crystallization scale-up strategy. So just a brief overview of the webinar. I'm going to touch on an overview of crystallization scale-up, some of the mixing implications and criteria for crystallization processes, some of the engineering calculations and how they're used to design an effective scale-up solution. And then I'm going to touch on two case studies. The first is a classical cooling crystallization where a process delivering variable PSD, and a second is a pH-adjusted crystallization where a solution of HCl IPA is added to a solution of freebase in IPA over a three-stage addition profile. And similarly, there's a variable output PSD, but also an undesired polymorph precipitating initially that also needed to be controlled. I'll then conclude with some comments and acknowledgements. In order to effectively scale up a crystallization process, it's imperative to understand the kind of mixing environment that you're operating in. And this mixing environment is heavily influenced by the type of stir agitator that's typically being employed. How that kind of agitator is sized relative to the vessel is typically critical, as it will affect the motion of the particles in solution. When performing experiments on the lab scale, they tend to be a lot easier to perform as kind of bad mixing is almost difficult to achieve. And plant scale equipment, generally contains baffles or unique impeller configurations, and there may just be limitations in the plant vessel in terms of what kind of sort of impeller can actually be utilized. And all of these things will directly kind of influence the agitation and kind of mixing environment that can be achieved, which in turn will directly influence the mass transfer, it kind of delivered in the process, which is obviously critical to a crystallization. Again, all of these can influence things like the shear of particles, how kind of reagents, anti-solvents are incorporated into the bulk. They can all affect the kind of crystal growth rate and the system's kinetics. And there are numerous kind of factors to consider in terms of the types of impeller, whether that be anchors or retreat curve impellers, baffles, the impeller diameters. All those sort of factors will heavily influence how that kind of reactor is mixed. But separately, and what's equally as crucial is the kind of crystallization conditions. So the crystallization kinetics will obviously directly influence the sort of kind of PSDs or particle size that can be delivered. But equally, how you go about seeding in terms of what type of seed you use, your seed loading, kind of where you're adding that seed in relation to the solubility curve in the phase diagram, your cooling anti-solvent profile, your kind of addition profile, whether that's close to the vessel wall or close to the impeller. All of these will have a direct impact on how your crystallization scales up. Our first case study is a cooling crystallization. It was the cooling crystallization of an API at a concentration of 370 mg a mil in 1.96 volumes of ethanol and 0.84 volumes of water. The material was dissolved at approximately 80 degrees before being cooled to 72 degrees, where it was then seeded. It was then aged for typically 4 hours, followed by cooling to 0 degrees. And two of the main issues identified were particle agglomeration observed at lab and plant under various conditions, and wide particle size distributions, PSDs, typically as a result of secondary nucleation agglomeration, particularly at the lab scale. So what we're looking at here is the reactor configurations typically used for this case study. So shown on the top is the 1 liter setup, which was a Mettler-Toledo 1 liter Optimax, which was equipped with a visco-prop impeller. Similarly, shown on the bottom is the plant scale vessel, which had an operating volume of usually about 490 litres. Again, it was equipped with a viscoprop impeller. In both cases, there was a number of PAT probes in situ. So there was FBRM, focus beam reflectance measurement, PVM, particle video microscopy, and IR, so infrared for measuring changes in the liquid phase concentration. What's given in the table on the right is some of the information on the solid and fluid properties, with information on the impeller and tank diameters for the 1 liter and plant scale reactors. So if we start off by taking a typical example of a 1 liter scale run, So what we're looking at here is a experiment that was tracked with FBRM, PVM, and ATR FTIR. And if we go from the image on the left to the image on the right, we're seeing the FBRM trends for a crystallization after dissolution has occurred at about 80 degrees. It's then cooled to 72 degrees where a seed is added. It's then aged for approximately 4 hours. And in the image on the right, what's apparent is after seeding, there's a significant amount of secondary nucleation occurring. And this is indicated by the changes in the kind of less than 10 counts being measured by the FBRM. And if we look at the corresponding PVM images along those kind of fixed points, there is kind of evidence of some kind of smaller particles clumping together to form these agglomerates. As the process reaches the end of the aging period and the kind of cooling portion of the process is initiated, there's actually evidence of a kind of some amount of agglomeration. And as that kind of cooling period is progressed, the agglomeration kind of looks to kind of come to a halt, and it reaches a kind of a steady kind of particle population. But then once the isolation temperature of 0 degrees is reached, there's actually evidence of further secondary nucleation, just indicated here, but again by the increase in the fine counts being measured by the FBRM. Throughout the process run, the IR, which is indicated in the blue trace, is tracking the desaturation rate pretty effectively. So you can see post-seeding, it desaturates and reaches a plateau, which then starts kind of decreasing once more during the kind of cooling portion of the experiment, again being tracked very effectively all the way to the isolation temperature. So what was apparent in kind of a typical lab scale run is that there was evidence of secondary nucleation post-seeding and throughout the aging period. There was some evidence of agglomeration, particularly when the cooling period towards isolation was initiated. And again, there was evidence of particle attrition, some growth in secondary nucleation during the kind of cooling to isolation. So one of the things we wanted to do was analyze the data sets available for the process that we're looking to optimize. So what's shown here are kind of two tables. On the top is kind of 5 experiments that were performed on the 1 liter scale using the viscoprop impeller. And on the bottom are 3 runs carried out in the plant scale vessel with the same impeller. Now, ideally, prior to carrying out these experiments, some kind of engineering calculation or kind of, mixing analysis probably should have been carried out. However, these kind of experiments were ran just with kind of variable RPM to understand, I suppose, the kind of effect of agitation speed on the kind of final product PSD that was being delivered from the process. So what we're seeing here is when the RPM was varied from about 250 to 650 on the 1 liter scale, and the RPM was varied from about 70 to 140 on the plant scale. There is kind of a kind of distinct difference in the PSDs being delivered. In general, the kind of D90s were a little bit larger on the plant scale, which was possibly just because of increased growth or potentially a little bit of a further agglomeration. But what was most noticeable was that the D10s were significantly reduced on the lab scale runs. You can see here in the plant scale, they were kind of roughly about 300 microns, but reducing to about kind of 200 microns or less on the lab scale. And what was also kind of readily apparent was that there was a decrease in the kind of overall D10 as the impeller speed was increased as well. And this wasn't the case on the plant scale. So just a very brief summary of the experimental observations that were kind of observed for the 1 liter and 490 liter scale experiments. There looked to be considerable differences in the final D10 on the lab and plant scale. In general, the D90s of the PSD looked to be kind of larger in the plant scale runs. And I think what the conclusion that was being drawn was that there was obviously some mixing differences or fundamental differences in the mixing environment that was attributing this difference in the final PSD. And one of the items that was highlighted was that despite the same impeller configuration being used, there was, I guess, like a very obvious difference in the impeller to tank diameter ratio, which was not kind of the same when going from the lab to the plant scale. So we wanted to understand the mixing environment a lot better in both the lab and plant scales for the process that we were looking to improve. So, typically when we're doing this, we look at, say, the kind of macro, meso, and micro mixing environments and the timescales associated with them in order to understand the kind of mixing environment a lot better. So, as a brief kind of summary or definition, macro mixing is generally the time taken to fully mix the reactor. Meso mixing is generally considered the time taken to incorporate a single drop being fed into the reactor into the bulk, and is usually much more relevant to the addition of anti-solvent and the characteristic kinetics of the process. Micro mixing, on the other hand, generally takes place on the molecular scale. Usually in this region, the mass transfer is dominated by molecular diffusion, and it's usually important for chemical processes with fast reaction kinetics. So without going into too much detail, just giving a kind of a brief summary of the kind of engineering calculations, the nuts and the bolts behind it. I won't spend too much time on it, but what's shown here is the typical kind of calculations or equations used to characterize scale up. So you have your Reynolds number, which describes the flow characteristics, your blade tip speed, which, as I mentioned, is the velocity around the kind of blade tip. You have your power input, which depends on your kind of power number, which is generally assumed from literature. You have your agitation speed and you have your impeller diameter, and we'll spend a bit more time on that in a second. You then have your mixing time, which is the time to completely mix a defined volume. And you have kind of two separate equations for that, and that's for turbulent flow and for transitional flow. In both of the case studies I'll talk through today, these are in turbulent flow. So in addition to the previous calculations, we have the equations for the mesomixing time scale, which is related to the kind of local velocity. And this is typically based on coefficients related to kind of feed location, whether it's headspace or subsurface addition, the impeller tip speed, feed time of your kind of anti-solvent or reagent, etc. And then what's shown on the bottom there is just some of the equations used for the kind of shear rate calculations. And in general, these are kind of, as I mentioned, related to the kind of power input per unit volume, the viscosity of the solution, and the stir speed being used in the reactor. So to begin with, typically in APC, what we do is characterize the kind of mixing environment through kind of these engineering calculations. So we can do these, I suppose, offline, just in kind of Excel sheets that we've developed internally. But a lot of the time we use kind of Dynachem to calculate these numbers for us. So what's shown here is just a summary table of the 1 liter Optimax with kind of impellers as per design spec. And in this case, for the viscoprop impeller, a power number was assumed from literature that was actually available within Dynachem. So all of the numbers shown here are for the kind of parameters mentioned previously. So power input per unit mass, Reynolds number, and tip speed. And these were carried out for a range of RPMs that were shown previously, so from about 250 to 650 RPM. So what's shown here is the final PSD from various runs that were performed at those RPMs shown. So there actually wasn't too much of a trend. In general, the kind of D90 decreased with increasing agitation speed and increasing shear and kind of power input, but the same trend wasn't kind of readily observed in the D10, for example. So we then looked at the kind of plant scale reactor. So similarly to the kind of 1 liter setup, we looked at the same kind of engineering calculations. And we used the same kind of RPM speed that we looked at previously. So from about 70 RPM to 140 RPM on the plant reactor. And when we actually kind of looked at the kind of output within Dynachem from these two setups, I suppose the only kind of two stir speeds that were, I suppose, kind of similar in delivering a kind of power input per unit mass was about 650 RPM on the 1 liter reactor and about 70 RPM on the plant scale reactor. And you can see the power input per unit mass was roughly kind of about 0.2 watts per kilo. And it also gave kind of fairly similar vessel turbulent shear rates and kind of similar-ish kind of impeller turbulent shear rates. And what we looked to do was just kind of compare the output PSD from these two runs, as I suppose they were kind of the most kind of relevant, and power input per unit mass is generally a fairly useful kind of scale up parameter to look at. But I suppose what was kind of immediately obvious from the final PSD was that they were quite different. So the D90, as kind of mentioned previously in the plant scale, was a little bit higher, although not too much. There was a significant difference in the final D50s. But again, it was the D10 that was really kind of significantly reduced. You could see there that the kind of final D10 was nearly kind of 60% less on the plant scale, even though that kind of power input per unit mass was fairly similar. And again, this just points to the possibility of kind of, maybe shear or secondary nucleation occurring on the lab scale, that's causing this reduction in the D10. So to kind of build on this, we generally use the engineering calculations and Dynachem, as I mentioned, to get an idea of how the relevant kind of scale up parameters are kind of affecting the crystallization. But what we also like to do at APC is use kind of CFD, which is computational fluid dynamics. So this allows you to kind of simulate and model the kind of reactor environment in kind of extensive detail, to give you an idea of kind of regions that might be kind of mixing limited, or regions of shear that might be causing particle attrition. So what we're looking at here is kind of the initial setup within CFD. So this is just taking the 1 liter reactor with the kind of 3 PAT probes, and the kind of impeller setup into kind of CFD to do a full geometric assembly. And this is kind of how the initial kind of stages of CFD are built. And similarly, what's shown here is the kind of geometric assembly for the plant scale reactor. So again, the viscoprop impeller with kind of 3 baffles, so to speak, or 3 PAT probes and a temperature probe. So once we have the initial elements of CFD constructed, we can then start looking at kind of some of the mixing profiles within CFD. So what's shown here are the velocity contours for a 1 liter and the plant scale reactors at 2 different kind of stir speeds. So 250 and 450 on the lab scale, and 100 and 140 on the plant scale. And what's kind of immediately apparent is that with an increase in the stir speed, you see kind of an increase in the velocity distribution close to the impeller, and that's the case for both scales. There are kind of more, I suppose, kind of dead zones, or kind of less kind of lower velocity gradients close to the impeller walls, which is not unexpected. But on the plant scale, you can actually see close to the impellers, there's regions of kind of high velocity kind of gradients, kind of indicated by red and yellow colorings. And that's reflected in the kind of higher P for V, or power input per unit mass values that were actually calculated earlier on as well. So similarly to the kind of velocity profiles, we can look at the shear rate distributions occurring in both of the reactor setups. And again, looking at the same stir speeds we looked at previously, what becomes kind of readily apparent is that for the lab scale reactors, particularly at increased stir speeds, there is kind of regions of higher shear, which is indicated by these kind of red kind of zones close to the impeller, that aren't really apparent on the plant scale at kind of either kind of stir speed that we looked at. And this may be a possible explanation as to why there was increased shear or increased secondary nucleation occurring on the lab scale. This kind of difference in the kind of shear rates that were being observed. So similarly to the shear profiles, when we looked at the kind of mixing profiles within each of the vessels, it was kind of readily apparent that there were kind of significantly higher, I suppose, kind of gradients kind of around the impeller on the lab scale. And you can see that the kind of downward velocities kind of around each of those impellers are kind of much greater than what's observed on plant, which is kind of a bit more, I suppose, radial and a bit more dispersed. There's also kind of a considerable more kind of vortex on the lab scale, and a vortex isn't always indicative of good mixing. But I think what we can kind of conclude from the CFD simulations was that there was just a kind of an increase, or probably more aggressive kind of mixing environment occurring on the 1 liter scale, that was maybe kind of subjecting some of the particles in that reactor to kind of greater shears or greater stress. So we then went and calculated this new kind of power number through CFD. And what's shown on the top left is the power number as a function of stir speed for both a 1 litre and a plant scale reactors. And additionally, we carried this out for a 3 litre reactor that was also available for work. And you can see that the kind of power number remains pretty much constant, which is what you would expect and hope. And when we kind of plot that as a kind of power input per unit volume as a function of RPM, you can see there the kind of change in P for V with increasing RPM, which is obviously kind of increasing as stir speed is increased. But what was most interesting was that the power number for the 1 litre impeller was found to be very similar to that assumed in the engineering calculations. However, for the plant vessel, it was actually about half of that value. So it came out at about 0.54 compared to an average of about 1.28 for the 1 litre reactor. So when we kind of summarized all these values into kind of, constant P for V and constant shear, which at this point look to be the kind of two, most likely candidates for kind of scale up criteria. We looked at these from kind of the 1 litre to a 3 litre and also the plant scale vessel. And we fixed the RPM speed for the 1 litre at 450 RPM. And then we just calculated through Dynachem the RPMs required to kind of match those P for V values for the kind of 3 litre and plant scale reactors, which was about 371. And similarly, we worked out the stir speeds required to match the constant shear rates, in this case the impeller turbulent shear rate, which is shown in the bottom there of about 1680. So in order to kind of evaluate the suitability of the standard engineering equations as a scale-up technique, we looked at the kind of engineering calculations to maintain a constant P for V or a constant shear, and we simulated them in CFD. And these were simulated across kind of 5 agitation rates at 3 different scales. And what's shown here is the distribution of the absolute and Y velocities in the top, and on the bottom is a distribution of the shear rate and the shear rate on a logarithmic axis. And what becomes kind of apparent here is that the velocities on the plant scale reactor are kind of significantly greater than in the kind of lab scale equivalent. And similarly for the kind of shear rate profiles, they appear to be quite different on the 1 litre scale, which is kind of the red trace here, compared to the 3 litre and plant scales. And it was suspected that this was possibly due to the kind of assumption of a similar impeller to tank diameter ratio being maintained, which was actually not the case. And even though the engineering calculation suggested that kind of constant P for V and constant shear was being arrived at, CFD simulations were suggesting that this was not the case. So when we actually looked at the kind of final PSDs from kind of 3 typical runs performed on the 3 different scales, you can actually see here in the bottom left is the correlation with kind of constant shear. And you can actually see for the kind of 3 litre and the plant scale vessel, these are actually being perfectly maintained. But on the 1 litre scale, even though the kind of maybe overall kind of D50 and D90 is kind of similar, there is a significant difference in the kind of final D10 being arrived at, which is indicated by the kind of hump here on the left-hand side of the PSD. And actually, when you looked at kind of constant P for V on the right-hand side, there was no real kind of obvious trend. The kind of PSD results were different across the 3 scales, which indicated that P for V was maybe not an ideal scale of criteria, but that shear may have some value. So in order to improve the kind of impeller to tank diameter ratio assumption, an impeller was kind of redesigned for the 1 litre Optimax. So it was the same visco prop impeller. However, it had a reduced diameter of about 42 millimeters on the 1 litre scale Optimax reactor. And this actually gave a kind of very similar impeller to tank diameter ratio. And once we had kind of achieved this, we then went and did a kind of recalculation of the engineering numbers. And what's shown here are the scale up calculations for constant shear. So you can see again for the 1 litre that was at 450, in order to maintain kind of constant shear with the 3 litre and plant scale vessels, this RPM had to be increased to 542 RPM. And as you can see here at the bottom, this gave kind of constant impeller turbulent shear rates for across the three vessels. So when we went back and actually re-examined kind of the shear rates across the three different vessel configurations, with the new impeller diameter, you can now see that the shear rate much more closely matches that of the 3 liter and the plant scale reactor. So you can see the original kind of shear rate distribution in red for the 59 millimeter impeller diameter at 450 RPM. And then moving to the left with the 42 millimeter impeller diameter at 542 RPM. They're now kind of much more closely matched. And similarly, when compared on the kind of log axis, you can see that they kind of overlay very nicely with the 3 liter vessel, and they're very closely matched with the plant scale vessel. And what this means then in I suppose kind of real terms is when we look at the PSDs once more, we have the kind of 1 liter kind of original 59 millimeter impeller diameter compared to the 3 liter and plant scale vessels. And again, you see this kind of fine hump in the red that was originally there. But actually, when we reran the experiment with this new kind of impeller diameter and stir speed to kind of match constant shear, you can see the significant reduction in the D10 as the kind of PSD trace goes from the kind of the red to the orange color. And that again is kind of reflected in the microscope images where the material is kind of a little bit more uniform. It's definitely larger, so there's an increase in the growth rate. And the level of kind of smaller particles is being significantly reduced now that the constant shear is being more kind of closely matched because of that, both the new power number and because of the improved kind of ratio. So I guess it highlights the importance of the geometric similarity in the engineering calculations, but also the usefulness of using CFD to kind of identify mixing limitations or regions where there might be kind of issues in the mixing environment, in order to kind of identify what the best kind of possible route is for scale up. And at the end of this case study, the recommendation for the process was to scale from the lab based on impeller turbulent shear rate, with an operating range for the plant vessel provided. So this brings us on to our second case study, which is, as I mentioned previously, was a pH adjusted crystallization whereby a solution of HCl IPA was added to a solution of freebase and IPA over a 3-stage addition profile. Again, the kind of final product was variable, and there was evidence of an undesired form precipitating prior to formed converting over a short time scale. And there were a couple of objectives to kind of deliver a controlled trajectory through the system's phase diagram, but also recommend a scale-up strategy that enabled the scale independent supply of the material within a CMO. And there were a number of issues, as I mentioned. So there was an undesired form precipitating initially. The final PSD was very inconsistent, and it appeared that the process was kind of mixing sensitive with an anchor impeller used on plant. So just as a very brief summary, there's just an idea of the kind of particle morphology that was being delivered at various scales. So we had a 1.5 kilo scale, a 6 kilo scale, and a 35 kilo scale. And what was kind of evident was that there was a deterioration in the product quality with an increase in scale, and that was reflected in the final PSD that was kind of reducing an overall D90 and D50 and D10. But really, it was just kind of apparent that the process was not robust, and there was issues, being encountered when an increase in scale was happening. So similar to the first case study, what's shown here is a lab scale experiment performed in a kind of 100 mil Mettler-Toledo EasyMax reactor system. And again, this was tracked with in situ FBRM, ATR, FTIR, and PVM. And what's shown here in the graph is the change in FBRM counts, but also the change in solution pH as the process occurs. So you can see it's a kind of fairly short runtime. It's typically complete within about an hour and a half. And as we kind of progress through the process, which is unseeded, we see kind of this kind of needle and kind of en bloc kind of crystals precipitating initially. This is kind of increased, or you see an increase in the FBRM counts after this, and there's kind of almost like a slight leveling off, and this again is probably because the population of particles is changing somewhat, from kind of more kind of blocky material and kind of longer needles. But at some point it reaches a kind of a maximum towards the end of the addition profile, where you see that the kind of population of needles in solution is actually converted to blocks, and essentially it's all kind of block material from that point on. So um, it was not an ideal route to have a kind of needle morphology precipitating initially. And it was apparent that the kind of final morphology was being affected by that kind of transition from one form to another as the process was carried out. So similarly to the first case study, we looked to kind of match the P for V that was being delivered on the kilo scale and the plant scale, in order to understand, if this had an impact on the final PSD, and could potentially be used as a scale of criteria. So what's shown here is a kind of summary of a number of different runs across scales and impeller configurations, all carried out at the same kind of fixed P for V. And what was kind of readily apparent was that even when the P for V was being matched, the kind of final D90 was still quite variable, and there didn't seem to be kind of any trend with respect to kind of P for V. However, when we looked at the meso mixing time, we started kind of identifying that the kind of heading towards the lower end of meso mixing time, around kind of 0.03 seconds. We were seeing that the kind of needle morphology was kind of precipitating consistently, and we wanted to avoid this, and we felt that the kind of precipitation was probably a function of kind of increased supersaturation levels and almost like rapid mixing that was occurring on that small time scale. And it was also highlighted on plant that the meso mixing time was approximately 0.3 seconds. And there was no evidence on plant that the needle morphology precipitated initially. But we felt that the meso mixing time was something to explore in further detail. So we targeted 3 experiments on the small scale, using kind of an easy max system, and we simply varied the agitation speed and the addition rate of the HCl IPA solution to target a kind of a low, middle, and relatively high meso mixing time, just to understand what the impact was on the final kind of PSD and particle morphology. And as you can see here, when meso mixing time is greater than what we looked at previously, kind of in or around the kind of 0.1 second region, were targeted, the particle morphology was fairly uniform and quite nice. And when the meso mixing time was increased higher to about 0.6, you could see the final material was quite heavily agglomerated. And we felt there was probably some relationship and a bit of a trend there that was worth kind of pursuing in greater detail. So we carried out some CFD analysis of a couple of plant scale configurations, just to understand if there were any kind of mixing differences between using kind of an anchor impeller and a retreat curve impeller, both of which were available to us as kind of choices. And what was identified was that with the anchor impeller, there was probably just a bit more potential for kind of dead zones or regions where the kind of HCl IPA would not be kind of as well incorporated, which might lead to kind of increased meso mixing times, and also kind of possible kind of regions where supersaturation might accumulate, and we wanted to avoid that scenario. And through the kind of looking at kind of the retreat curve impeller, it looked to be kind of a lot more well mixed. That there was no kind of regions of kind of hold up or dead zones. And from the CFD, we felt that the retreat curve impeller might be a more kind of useful configuration to use at scale. So we carried out a number of process runs on the 1 liter scale at APC, all kind of targeting various meso mixing times. And again, this was kind of to highlight the kind of change in particle morphology that would be delivered as a function of changing meso mixing time, but also to observe if the needle morphology precipitated initially. And what was apparent was that the particle morphology changed considerably through a change in the meso mixing time. But more importantly was that when kind of meso mixing times of about kind of 0.1 or greater were targeted, the kind of desired block material was initially precipitating, which is what we wanted. But you can see that when meso mixing times greater than 0.1 were targeted, the final morphology kind of varied very quickly once that was increased. So you can see when a time of 0.1099 seconds was targeted, we got this nice uniform block material, and there was no evidence of needles precipitating initially. But when we actually increased that further, even though the material was relatively uniform, it started decreasing in size, which is not what we wanted. But it was a good kind of result to see that the kind of needle morphology could be avoided while still kind of maintaining this kind of uniform population of particles. So we were happy that kind of meso mixing times of around kind of 0.1 seconds were what should be targeted. And in order to demonstrate that further, we did a couple more kind of scale up runs. So we did one run on a 5 liter scale, again matching a very similar meso mixing time. In this case, it was about 0.11. And what you can see here is the final PSD and microscope images of the material afforded from that run. So on the left, you have the 1 liter scale process carried out. In the middle is the 5 liter scale. And on the right is kind of typical morphology afforded from a kilo scale run. So even though the overall particle size is slightly changing, the general population is very, very uniform, and there was no evidence of the needle morphology precipitating initially. So it was the recommendation to scale up based on kind of targeted meso mixing time in order to deliver that kind of uniform population of particles, which is what was desired. So just some concluding remarks. As you can see from the two case studies presented, crystallization scale-up is a fairly complex process. What was looked at today were two examples where kind of mixing was the kind of dominating factor for scale-up, but equally, things like seeding or how you seed, your cooling addition profiles, solvent ratio, etc., can all be kind of troublesome and typically have to be examined. But engineering calculations are a really useful kind of, I suppose, like a navigation tool at understanding, what kind of scale-up criteria might be the most relevant to your process. But they do have their limitations, as I've demonstrated. And where these kind of limitations occur, things like CFD or other kind of mixing software packages can really help identify, what the kind of best next steps are in order to kind of design a robust process. And both of these can be really aided by PAT, which is kind of commonly used now, both in kind of lab and plant scales, to really identify, what the issues are in the process, and kind of help as a bit of a guide to kind of determine, what needs to be looked at or what the most kind of relevant criteria are to be examined. But ultimately, it's probably a combination of all three is really required to, really kind of design a robust scale-up strategy. And hopefully these two case studies have given you an idea of how to go about that.